All right, welcome to lecture on chapter 7, everybody. Let's walk through that. So here we go. And there are absolutely some worksheets here. I'll probably continue to explain some more worksheets. Let's go ahead and start off here. So probability in samples, the distribution of sample means. So the first thing we're going to look at is we want to define distribution of sampling means. We want to describe distribution by shape, expected value, and standard error. We want to describe the location of the sample mean, M, by the z-score. We want to determine probabilities corresponding to sample mean using z-scores and the unit normal table. Tools you'll need: random sampling, chapter 6, probability and normal distribution, chapter 6, z-scores, chapter 5. The location of a z-score, so samples, populations, and the distribution of sample means. The location of a score in a sample or a population can be represented with a z-score. Researchers typically want to study entire samples rather than single scores. The sample provides an estimate of the population. Procedure for transforming a sample mean to a z-score. We're going to walk through all of that. So sampling error. A sample provides an incomplete picture of the population. Sampling error is the natural discrepancy or the amount of error between a sample statistic and its corresponding population parameter. Error does not indicate that a mistake was made. Samples are variable. Two samples are very rarely identical. Two separate samples will probably be different, even though they are taken from the same population. Given a random sample, it is unlikely that the sample means would always be the same. The distribution of sample means is the collection of sample means for all the possible random samples of a particular size n that can be obtained from a population. Distributions in earlier chapters were distributions of scores from samples. A sampling distribution is a distribution of statistics, not scores. The distribution of sample means is obtained by selecting all the possible sample sizes, all the possible samples of a specific size or n from a population. The sample mean should pile up around the population mean. The distribution of sample means is approximately normal in shape. And if you remember, we did that video of the dance of the means, and I will see about possibly posting that as well. In fact, let me see if I can do that right now for you guys. It's under show, stop share. Let's continue here. All right, so characteristics of the distribution of the sample means. The sample means should pile up around the population mean. Play with that dance of the means that I sent you. That will show you exactly what I'm talking about. There's a link posted in the news items. The distribution of the sample means is approximately normal in shape. The larger the sample size, the closer the sample mean should be to the population mean. Figure 7.2, frequency distribution histogram for a population of n equals 4, scores 2, 4, 6, 8. The distribution of sample means for n. The distribution shows the 16 sample means from table 7.1. It is possible to determine exactly what the distribution of sample means looks like without taking hundreds or thousands of samples. The central limit theorem is used to specify the shape, central tendency, and variability of the distribution of sample means. The central limit theorem applies to any population with a mean and standard deviation. Distribution of sample means approaches a normal distribution as n approaches infinity. Distribution of sample means for samples of size n will have a mean of the sample. Distribution of sample means for sample size n will have a standard deviation of the standard deviation divided by the square root of n. The distribution of sample means is almost perfectly normal in either of two conditions. The population from which the samples are selected is a normal distribution, or the number of scores n in each sample is relatively large, at least 30. The mean of the distribution of the sample means the expected value of m. The mean of the distribution of the sample means is the mean and has a value equal to the mean of the population scores. The mean of the distribution of sample means is called the expected value of the mean. Mean the M is an unbiased statistic because mean subset M, the expected value of the distribution of the sample means, is the value of the population. The standard error of the mean measures how well an individual sample mean represents the entire distribution. Variability of a distribution of scores is measured by the standard deviation. Variability of a distribution of sample means is measured by the standard deviation of the sample means and is called the standard error of the mean, and is written as the error of the mean, like that, theta subset M. The standard error of the mean is the standard deviation of the distribution of sample means. When it is large, the means are widely scattered. The standard error of the mean provides a measure of how much distance is expected on average between basically the population mean and the sample mean right here and the population mean. The dance of the means will make that clear if you play with that link I put in there. The law of large numbers: the larger the sample size and the more probable it is that the sample mean will be close to the population mean. Population variance: the smaller the variance in the population, the more probable it is that the sample mean will be close to the population mean. The relationship between standard error and sample size: as the sample size is increased, there is less error between the sample mean and the population mean. Figure 7.5, three distributions. Part A shows a population of reading scores. Part B shows a sample of n equals 16 reading scores. Part C shows the distribution of sample means for all possible samples of n equals 16 reading scores. Note that the mean for the sample in part B is one of the thousands of sample means in the distribution shown in part C. Learning check 1 of 2. A population has a mean of 60, the standard deviation of 5. The distribution of sample means for sample sizes n equals 4 selected from this population would have an expected value of what? 5, 60, 30, or 15. Feel free to pause me, calculate that formula. There are master formulas that are posted. Probably do a worksheet towards the end of this lecture as well. So our answer is 60, a population with a mean of 60 and the distribution of sample mean, standard deviation of 5, sample size n equals 4, selected from this population would have an expected value of 60. Decide if each of the following statements is true or false. True or false: the shape of a distribution of a sample means is always normal. True or false: as sample size increases, the value of the standard error decreases. False: the shape is normal only if the population is normal or n is greater than or equal to 30. True: sample size is the denominator of the equation, so as n grows larger, standard error decreases. Z-scores and probability for sample means. Their primary use for the distribution of sample means is to find the probability of selecting a sample with a specific mean. Proportions of the normal curve are used to represent probabilities. A z-score for the sample mean is computed. A z-score for sample means: the sign tells whether the location is above or below the mean. The number tells the distance between the location and the mean in terms of the number of standard deviations. The z-score formula is equal to mean, the new mean, like the sample mean, minus the old mean, the population mean, over the standard error. This is the distribution of sample means for n equals 16. Samples were selected from a normal distribution with a mean of 500 and a standard deviation of 100. Figure 7.7, the middle 80% of the distribution of sample means is equal to n equals 25. Samples were selected from a normal population with a mean of 500 and a standard deviation of 100. More about standard error. There will usually be a discrepancy between a sample mean and the true population mean. This discrepancy is called sampling error. The amount of sampling error varies across samples. The variability of sampling error is measured by the standard error of the mean. Figure 7.8, an example of a typical distribution of sample means. Each of the bars in the histogram represents the frequencies for different sample means. A curve for the normal distribution is superimposed on the histogram. The expected value of the distribution of sample means equals the population mean. Here we have figure 7.9, the distribution of sample means for A, n equals 1, B, n equals 4, and C, n equals 100, obtained from a normal population with a mean of 80 and a standard deviation of 20. Notice that the size of the standard error decreases as the sample size increases. Reporting standard error. Journals vary in how they refer to the standard error, but frequently use the standard error and the standard error of the mean. It is often reported in a table along with N and M for the different groups in an experiment. May also be added to a bar line or line graph. Here we have the mean score plus or minus the standard error for the treatment groups A and B. Here, figure 7.10, the mean and number of mistakes plus or minus the standard error for groups A and B on each trial. Looking ahead to inferential statistics. Inferential statistics use sample data as the basis for drawing general conclusions about populations. Sample information is not a perfectly accurate reflection of its population or sampling error. The natural differences between samples and populations introduce a degree of uncertainty and error into all inferential processes. Figure 7.2, the structure of the research study described in example 7.7. The purpose of the study is to determine whether the treatment, a growth hormone, has an effect on weight for rats. This is figure 7.13, the distribution of the sample means for samples of n equals 25 for untreated rats from example 7.7. A random sample of n equals 16 scores is obtained from a population, the mean of 50 and a standard deviation of 16. If the sample mean is equal to 58, the z-score corresponding to the sample mean is what? 1, 2, 4, or cannot determine? Your answer is 2. Decide if each of the following statements is true or false. A sample mean with a z-score of 3 is a fairly typical representative sample, or the mean of the sample is always equal to the population mean. False. A z-score of 3 is an extreme or unlikely z-score. False. Individual samples will vary from the population mean. If you have questions, thoughts, concerns, please do reach out. All right, and let's do a little bit of review through some of the stuff we've been talking about so far. So, a sampling distribution is a distribution of all sample means or sample variances that could be obtained in a sampling distribution, samples of a given size from the same population. Sampling without replacement is a method of sampling in which each participant or item selected is not replaced before the next selection. This method of sampling is the most common method used in the behavioral sciences. Sampling with replacement is a method of sampling in which each participant or item selected is replaced before the next selection. This method of sampling is used in the development of statistical theory. Let's find the probability of selecting a triangle marked B on the first draw of 10 other triangles with a total of 2 triangles marked B. The rest of the triangles are marked C. We would use the following formula, but first remember that P is equal to probability. So P, the triangle marked B on the first draw, is 2 divided by 10, or 0.20, or a 20% chance. Second draw, we do not replace the triangle marked B. If we selected the triangle marked B on the first draw, then only 9 triangles remain, one of which is marked C. The probability of selecting the triangle marked C is the number of triangles marked B divided by the total number of triangles remaining on the desk. Therefore, the probability of triangle marked B on the second draw, it's 1/9 or 0.11 or 11% chance. So the next thing I ask you to do is, using this exact same formula, calculate on your own the following without replacement. What's the probability of selecting a circle marked D with 3 circles marked D out of a total number of 15 circles, with the remaining circles marked E? Show your work. And then if you do not replace the first circle you just selected marked D, and you want to select another circle marked D, what is the new probability? Show your work. You can literally look at the example and use the same steps, and you'll absolutely get there. If you have questions, reach out to me. If you want me to record a walkthrough or a live session on the thing you do on your own, I'm absolutely down. I just need to know everybody. More definitions. A sample design is a specific plan or protocol for how individuals will be selected or sampled from a population of interest. FYI information. In theoretical sampling, the order of selecting individuals matters, and each individual selected is replaced before sampling again. In experimental sampling, the order of selecting individuals does not matter, and each individual selected is not replaced before selecting again. Example, a researcher selected a sample of 4, n equals 4, from a population size of 11. Using the sample example, how many possible samples of 4 can be used using experimental sampling? So the following formula: N, capital N, population, exclamation point, small n, sample, exclamation point, times n minus n, exclamation point. When you plug that formula in, we plug in n for the population. The sample size looks like the following: 11, exclamation point, 4, exclamation point, times 11 minus 4. The breakdown is like this: 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 4 times 3 times 2 times 1 times 7, which is right here, times 5 times 4 times 3 times 2 times 1. This equals 330, which is the total number of samples possible. On your own, calculate the same thing. So just reference this formula using the sample size of n from a population of 9. Just plug that in the way I just did it. And then using that example, how many possible sample sizes of 2 can be selected using experimental sampling? Next, create your own experimental sampling exercise based on hypotheses. Actually, just create your own sampling exercise. We won't even say based on hypotheses. So just come up with like a scenario like what I did, and you can frame it based on the examples here. Some definitions and FY information to review. An unbiased estimator is any sample statistic, such as the sample variance, when we divide the SS, or the sum of the squares, by n minus 1 obtained from a randomly selected sample that equals the value of its respective population parameter, such as population variance on average. The central limit theorem explains that regardless of the distribution of scores in a population, the sampling distribution of sample means selected at random from that population will approach the shape of a normal distribution as the number of samples in the sampling distribution increases. FYI, the sample mean is an unbiased estimator of the value of the population mean. The central limit theorem explains that the shape of a sampling distribution of a sample means tends towards a normal distribution, regardless of the distribution in the population. Theoretical sample overview. In behavioral research, we often measure a sample mean to estimate the value of a population mean. To determine how well a sample mean estimates a population mean, we need to identify a population of interest and then determine the distribution of the sample means for all possible samples of a given size that can be selected from that population. Thus, we need to construct a sampling distribution. Because statisticians use theoretical sampling to learn about the characteristics of the mean, we will also use this sampling strategy to select samples from a population. We can use the sampling distribution we construct to see how well as the sample mean estimates the value of the population mean. Theoretical sampling exercise. To construct a sampling distribution, let's identify a hypothetical population of 5 people, n equals 5, who took the Ocean personality test and assumed they had the following quantitative scores. Person A had 12, B 20, C 7, D 8, person E scored 9. Because we know all 5 scores in the population, we can identify the mean in this population. Then we can construct a sampling distribution of the mean to determine how the sample means could be selected from this population compared to the population we calculated. The population mean for n equals 5. The population mean is computed by summing all the scores in the population, then divided by the population size. So 12 plus 20 plus 7 plus 8 plus 9 divided by 5 equals 11.2, which is our population mean. Then I ask you to do the same thing with the next scenario, and then create a theoretical sampling exercise of your own. We're just trying to calculate the mean here. Some important implications of the central limit theorem. The central limit theorem has an important implication. It means that the probability distribution for obtaining the sample mean we could select from a population is normal. From the empirical rule, we then know that 95% of all possible sample means we could select from a population are within 2 standard deviations of that population. All right, and that concludes our lecture on chapter 7. Hope that information is helpful. I'll post the lecture on chapter 8 shortly here. And I hope you learned something. Ask questions. I'm explaining a lot of the worksheets here. If there's any worksheets you're unclear on or want some help on, I'm happy to meet one-on-one. I might want to record it. I'm happy to do live sessions. I just need to know everybody. Until I hear something definitive from both members of the class, I will keep recording these and getting these posted. I look forward to seeing your work and hope you learned something. And I look forward to recording another video for you shortly. Take care.